This is a solubility problem. The insoluble compound is calcium hydroxide. First we want the molar solubility in pure water. We're given KSP. So we write out the equilibrium expression. And we know that KSP will be equal to calcium 2 plus ion concentration and the hydroxide ion concentration squared. In our ice table, the solid doesn't appear. Initially, we assume we don't have any of either ion. We're going to gain S and 2S for every mole of calcium hydroxide that dissolves and thus dissociates. So we have S and 2S here. Our KSP value expression, we have S times 2S times 2S. It's going to be 4S to the third. Alright, so we want to find this molar solubility so we can, actually it's the focus is to get the molar solubility. So we have S cubed is going to equal KSP divided by 4. Again, we're after the value of S. So we're going to take the third root of S cubed, which is the same as raising it to the 0.33333 power. We take the value of KSP that we're given, plop that into our equation, and we get S is 1.176 times 10 to the minus 2. So with two sig figs, that's 1.2 times 10 to the minus 2, or if you want to, we can rewrite that as 0.012 moles per liter. Okay, so that tells us every liter of pure water will have this number of moles of calcium hydroxide dissolved in it. Alright, now we move on to a common ion problem. Calcium nitrate is a soluble compound. All nitrates are soluble. It's going to dissolve and then dissociate to give us calcium ions and nitrate ions. The nitrate ions we don't care about. They don't interfere with the equilibrium, but the calcium ions certainly do. So if we start with 0.1 molar calcium nitrate, we know that we have an initial concentration of 0.1 moles per liter of calcium ions. Alright, so we need to be careful constructing our ice table here because we have an initial concentration of one of these ions. Initial change equilibrium. Okay, initially we have some calcium 2 plus. So we start with 0.1. And then we assume we don't have any hydroxide. When 1 mole of calcium hydroxide dissolves, we generate S and 2S moles of our products. So initial plus change gives us equilibrium. So we can write KSP is equal to calcium 2 plus times hydroxide squared. This is 0.1 plus S, and this is 2S quantity squared. Alright, and we can rewrite this as 0.1 plus S times 4S squared. Alright, so this is one instance, I think, where it's beneficial instead of solving this, we can make our, instead of solving this via recursion, we can likely make the approximation that S is small compared to 0.1 plus S. Alright, so we can check first by multiplying 1,000 times our KSP. 1,000 times our KSP KSP is given here at the top. So this is 6.5 times 10 to the minus 3, or we can rewrite this as the following. We can make our approximation if our concentration that we're comparing S to is larger than this value. And here we have 0.1 is going to be larger than 1000 times K, so you can make that approximation. That this is approximately equal to 0.1 times 4s squared. Okay, all we did here was prove that it was okay to make this approximation that 0.1 plus s is essentially 0.1, that s is negligible compared to 0.1. Alright, so you can solve for s now, as s squared is going to be KSP divided by 0.1 and 4. If we take the square root of that, we get s. So if we put in our value of KSP, churn this out, our value for s is 0.00403. So let's compare these two values. Pure water, we have a solubility of 0.012, and a little bit of the common ion, the solubility is much lower. Alright, so let's continue and consider a solubility problem where we have sodium chloride instead of pure water as our initial solution. So you have sodium ions and chloride ions in solution. If we look at calcium hydroxide dissociation, okay, our equilibrium involves calcium and hydroxide ions. Neither of these ions will either react with water or participate in this equilibrium. So we have no common ions. The result is that the solubility in sodium chloride aqueous solution is the same as pure water, which is S was 0.012 moles per liter.